Hi guys, so I'm going to do a few practice problems today on empirical formulas. Stay tuned for a video about molecular formulas soon, but I personally think empirical formulas are a little bit easier to learn first. So what even is an empirical formula? Basically, an empirical formula is the simplest whole number, it's really important, ratio of elements. What's a molecular formula? Your molecular formula is going to be the actual representation of elements in a compound. In case that kind of went over your head, let's look at glucose as an example, C6H12O6. Okay, the empirical formula of glucose is going to be the simplest whole number ratio. So if we're looking for a whole number ratio and we want to simplify that, it's going to be like a fraction where we can divide by the common number. We can divide all these by 6, and we'll get C1H2O. That's the empirical formula. The molecular formula is just simply glucose as it is. And this is its actual chemical formula. But empirical formulas, sometimes we get really, really big compounds and we want to simplify that. So that's what we use empirical formula for. A way to kind of remember is, I think of empirical formula, if you sound it out, you can kind of hear empirical, kind of like pure in the word. And pure just means it's purified. It has the simplest whole number. The numbers are divided as much as they can. It's a pure chemical formula. So let's look at a few examples here. The number one most important thing to remember is that if we're given percentages, if we're given grams of certain elements, we always need to change them to moles. So in this case, we're given mass percent compositions, and don't be fooled by these, because 75.69% carbon is the same thing as 75.69 grams of carbon. Now, to get from grams to moles, we already know that we can use molar mass as our conversion factor. Oops. And we know that if we look at the periodic table, there's 12 grams of carbon per every 1 mole. Awesome. Now we are already in moles of carbon. Easy, right? And this should be 6.3075 moles of carbon. If you're quick at converting from grams to moles, then this is going to be pretty simple for you. Let's go to hydrogen next. 8.80% hydrogen is the same thing as 8.80 grams of hydrogen. The molar mass is 1 gram of hydrogen per 1 mole of hydrogen. And now we just have 8.80 moles of hydrogen. Lastly, we have oxygen. 15.51% of oxygen is the same thing as 15.51 grams of oxygen. The molar mass according to the periodic table is 16 grams of oxygen per 1 mole of oxygen. When we multiply that out, we should get 0.969 moles of oxygen. Now, when you see a chemical formula like this, the little subscripts right there represent moles, not grams. But here we can see that these are not whole numbers, so we need to do something to get them to whole numbers, so we can get an acceptable empirical formula here. And the way to do that is to divide the numbers by the least amount of moles that you see here. So we can divide the moles of oxygen by 0.969 moles. And we can do the same thing for hydrogen and carbon. Again, just dividing all the elements by the least amount of moles that you see out of all of them. When we divide these all, we should get whole numbers, and that's going to give us those little subscripts that we need in the formula. So we have 1 mole of oxygen. We have 9 moles, again I'm just dividing here, of hydrogen, 6.5 moles of carbon. We have 2 whole numbers here, which is what we want, and we have 6.5, which luckily we can multiply anything that's 0.5 by 2 to get a whole number, and I'll show you what I mean by that. If we write out our elements here, CHO, we know that the number of moles equals that amount of the element that we see in a chemical formula. And, oops, C is 6.5, H is going to be 9, and O is going to be 1. We don't typically write the 1, though. For this, we need to get rid of 6.5 because we can't have a non-whole number in a chemical formula. So we're going to multiply the whole thing by 2. Just distribute that 2 to all the subscripts we see there. And our answer is this, which 6.5 times 2 is 13 here, 2 times 9, 18, and then lastly, 2 times 1 is 2. This is our empirical formula. This is also the molecular formula. And the reason is because we can't simplify these numbers. We can't simplify all these numbers even more. The next one here we have, we're given milligrams. We're not given mass percent. And we're given the total milligrams of the chloride. Something that is called a chloride, that just is the name of an element with chlorine in it. So we know that 6.61 milligrams is our total mass of this nitrogen chloride. And we don't know the empirical formula for this. So it's N something Cl something or other. And we don't know what that X and Y is yet. That's what we're going to find. But we do know that there's 0.77 milligrams of nitrogen. Let's find how much chlorine we have. There's some simple subtraction here. And we should get 5.84 milligrams. We know this is chlorine because we subtracted. From here, remember what I said, we want to get to moles. Oh, this is nitrogen. Okay. We're going to use molar mass as our conversion factor. We know from the periodic table that there's 14 grams in 1 mole of nitrogen. I did skip ahead, though. We have milligrams here. And in order to use molar mass, we know that we have to have grams, right? So just this simple conversion factor. You can even do this in your head. Perfect. So now our milligrams cancel out and we have grams. Now we can use that molar mass conversion factor. In the periodic table, we know that there's 14 grams of nitrogen per 1 mole of nitrogen. Perfect. Grams cancel out. We're left with moles of nitrogen, which is what we want. If we multiply that out on our calculator, we should get 5.5 times 10 to the negative 5th moles of nitrogen. We're not done yet, though. On this side, we know that there's, I believe it's 34 moles. I'm trying to remember this from memory. 34 moles of chlorine per 1. Oh, that's backwards. 35 grams chlorine per 1 mole of chlorine. These two cancel, and we're left with 1.7 times 10 to the negative 4th moles of chlorine. Since these are not whole numbers, like I said in the previous example, we need to divide them both by the smallest number of moles available here. And that is 5.5 times 10 to the negative 5. Luckily, we get a nice clean number here, which tells us that we did our math correctly. We just divide this by itself to get 1. And our chloride here, we have, remember, like I said, NXCLY. Our X is going to be that 1, but we don't write a 1. And our Cl is going to be that 3. Perfect. This last one is really straightforward. I'm going to blow through this a little bit more quickly because we already have everything in moles. We don't need to do any converting here, luckily. We have 5.4 moles of carbon. 7.2 moles of hydrogen, 1.8 moles of nitrogen. This is a good recap example to show that we understand how to find an empirical formula, and we know from the past two examples that we divide by the smallest number of moles here.